So let's talk about another idea related to energy. So let's think about two vehicles, right? Let's do a minivan. Sure. How do you draw a minivan? And a sports car. Sure, spectacular. Let's let those have the same mass. And let's ask about 0 to 60. Right? So what is 0 to 60? Well, it's you usually measure a time, right? Associated with how long when you floor it, you push the accelerator down all the way. How long does it take the car to go from 0 miles per hour to 60 miles per hour? So they're both going to do this. Right? 0 to 60 eventually. I can do better. So I've got a V final here of 60 miles per hour and a V final here of also 60 miles per hour. And the question is, which one has more energy at the end of this motion? Which one has more energy at the end of this motion? And the answer is, well, it feels like they should do this motion differently, right? A sports car and a minivan are two different things. Even if they have the same mass going in the final same speed, something about this motion is different. But it's not the energy change, right? So K final is the same for each. So delta K, I could say, is the same for each. So what's different? Well, it's what we measure for 0 to 60, right? It's a time. We could say, but delta T is different. Right? I expect the minivan to do this eventually, but the sports car should do it quickly. So delta T, we'll say sports car is small. And delta T for the minivan is big. Okay. Okay, so how do we quantify the difference in these motions? Well, the answer is this is a rate, right? If we're talking about a delta T, then we're talking about a rate. So a rate of energy transfer, right? Either energy usage or energy absorption. Rate of energy transfer is something we call power. And power is just delta E of whatever kind divided by delta T. Right? So that the power delivered to the car by the car's engine for the sports car is big because I'm dividing by something small, and the power delivered to the minivan by the minivan's engine is small because I'm dividing by something bigger. So and that tracks, right? When we think about engines, we talk about horsepower. Horsepower is a unit for the rate of energy use, right? Or rate of energy delivered. But horsepower is not the SI unit, right? The SI unit for this needs to be joules per second, right? Because upstairs here is a joule and downstairs here is a second. We define this as a watt, or capital W, which is confusing because capital W is the variable name for work, which could be the numerator of power, because work is equal to delta E. But that's just what it is. You may recognize a watt from maybe a light bulb, right? Light bulbs use energy, and a 60-watt light bulb versus a 100-watt light bulb are different, right? They're plugged into the same voltage. Right? When you turn on a switch, 120 volts is delivered to it, but a different amount of current is drawn by each one, so they use different amounts of power. And you notice a brightness difference, right? The brightness of the 100-watt bulb is higher than the brightness of the 60-watt bulb. So they indeed have different powers, right? So their labels are correct. Yeah, so let me mention one other thing. I drew these cars going the same distance. They wouldn't, right? The sports car ought to do this faster, so it's accelerating faster, so it ought to go a smaller distance to get to this 60 miles an hour, whereas the minivan is having to travel further to get up to 60 miles per hour. Just as a matter of an aside. So let's talk about let's do an example. So I'm going to look at example number 11. Has a skier pulled up a frictionless slope by a tow rope that makes an angle of 12 degrees with the horizontal. The rope moves parallel to the slope with a constant speed of 1 meter per second. And the force of the rope does 900 joules of work on the skier as it moves the skier up 8 meters up the incline. So let's just draw that picture for starters. Right? It's a good place to start. So I'm probably going to exaggerate the 12 degrees. That's bigger than 12 degrees. But it's shallow, right? That's pretty okay. So then we need a skier. Holding a tow rope. There's my skier. And I could draw the rope there, and that's attached to, something that's pulling the rope up there, and it's pulled, let's see, he's pulled with constant speed, so I could say there's V, and the length of the incline, that delta, we'll call it delta X, is 8 meters. And we're told that the work done in this motion is 900 joules. Okay, so we could do some math with it, but maybe we'll do that in a minute. So let's ask the question, if the rope moved with a constant speed of 2 meters per second, how much work would be done by this force? Okay. So we have to think about that. If the skiers pulled up this slope at a faster rate, is there more work done? Right, so there are three kind of, like, I guess it could be this, I guess it could be that. There are three guesses to this, and that is the work doubles, the work halves, or the work doesn't change. So let's not start by guessing, right? But again, those are the things that kind of make gut sense, because clearly something is changing. But think about the work done here. So the work energy theorem tells me work equals delta E. Right? What kind of energy is changing in this motion? Well, the speed is constant. So if I write delta E as delta K plus delta U, delta E is 0 because the energy's not changing, or sorry, the speed's not changing. So that leaves delta U. What kind of potential is changing here? Well, it's gravitational, right? Because you're moving up this incline. And no matter how fast you're going up this incline, the change in height, this delta, like Y, or delta H, let's call it a delta H. No matter how fast you're going up or down this, up this slope, delta H is the same, right? So delta H is the same for for 1 meter per second and 2 meters per second. So the answer to A is work depends on delta H, not V. So work is 900 joules. Right? We're not changing our how we're changing the height. So the work done here is the same as it was at 1 meter per second. But the rate at which that energy is delivered actually does go up by a factor of 2. Right? So let's ask that question then. At what rate is the force doing work at 1 meter, or 1 meter per second and at 2 meters per second? Right? So the questions for B and C are what is the power? Because remember, power is a dE or a delta E over delta T. That's a rate, right? Delta something over delta T is a rate. So we could plug into that. But how do we define power? As an aside, right? Power is delta E over delta T. But I don't know a delta T for these. And I could figure out a delta T given the distance we're traveling and maybe the work done, but I'm going to have to think about that kind of critically. But what we could do is say, well, look, the delta E here really is work. It's force over some distance over a time. But do you notice that? Delta X over delta T, that's a V, right? So I could write this as force times a velocity. That is useful. That is a useful equation for us to have. So I know the velocity for each of these. For B, it's 1, and for C, it's 2. But what is the force acting here? What is the force acting here? Well, so this will be our aside. So if I can find that, then I can find the power. So what is the force acting here? Well, there are several ways to do this. One would be to draw a free body diagram and recognize that that the force supplied by the rope has to match the x component of gravity. But there's an easier way to do this, because again, work equals force over a distance, and I know the distance up the slope is 8 meters is 8 meters. And I also know the work done, because it was given to me, is 900 joules. So look, the only thing I don't know is this force. So I can use this to solve for the force. Again, if that's tricky to you, you can draw a free body diagram and figure out what force has to be acting against the x component of gravity. So F times 8 meters equals 900 joules. And what I get for that force is 112.5 newtons. Okay, maybe I shouldn't box that because that's not my final answer. But now that I know the force required, that's the same force for A and B. It's the same force for A and B because I don't have to pull harder to keep it moving. I have to pull hard for a moment to get this to speed up. But once it's at speed, it doesn't have to. You don't want to accelerate anymore. So so let's plug that in. We're almost there. So the answer to B then, it's power equals force times a velocity. The force is 112.5 newtons times 1 meter per second. Right, is 112.5. Let's round it to 113 Newton meters per second. A Newton meter is a joule, so that's a joule per second, and a joule per second is a watt. So I can write this as watts. And in letter C, power is still force acting over, force times the velocity. The force didn't change, it's 112.5 newtons, but the velocity is now 2 meters per second. So the power really is twice as much. It's 225 if we round that, 225 watts. Okay,